Hello? Okay. So the midterm is on Tuesday, and so today I will just answer questions and go over my notes and generally give you whatever advice I can give. It's actually a, yes, already. Sorry? No. So I'll be, no, old-fashioned. It's actually a dangerous time for me to be coming here and lecturing because I just prepared the midterm like 5 minutes ago. So do you know what cold calling is? Like, you know, these mentalists have these tricks where they ask you questions and based on your tone, they're able to tell answers. So you might ask me, is this going to be on the exam? And I'd say no. I could say no to everything. But depending on my tone, maybe you can detect what is actually on the midterm. I hope not, but maybe. So for those of you with DRC accommodations, you should be hearing something from the department on that. And if not, by Monday, I will probably send you, I'll try to book some rooms and that would be available. The exam is not meant to be long. I mean, you can use the entire 90 minutes for it. I sort of prepared it as a 1-hour exam, but you all have 90 minutes. It will be multiple choice entirely. But you have to give an explanation for every answer, so you can't guess. Okay, and yes. How many? 50. Yes. I'm kidding, it's not 50 questions. I'm just messing with you. Yeah, no, do you what? There will be questions about pointers, yes. I'm not going to make you code, though, because it's multiple choice, so you don't have to know syntax, right? Yeah? Sorry? You get no points then. You have to give an explanation. Otherwise, you could just randomly guess, and most of you would get at least 30% of the score. So what I thought I'd do is I just have all my notes, and we can just go over it, and you can ask questions wherever you see something. Yeah. Sure, I will do that as we proceed. Yes?
Are there any like C questions?
Yes. Pointers. Yeah?
It's still like open everything, right?
Open everything, bring whatever you want. No electronic devices, but you can bring the book, you can bring the notes. Before I used to have a policy where I'd say you can only bring your notes and you shouldn't bring a textbook, but then people would ask all these like smart-ass questions like, oh, could I photocopy the book or a chapter or write it down? So I said, forget it, just bring whatever you want. No, I don't want to deal with it. That's usually bad news, which means that I have to come up with questions whose answer will not be in the book, right? So anyway, so the way we started was with the n-queens problem, which hopefully by now all of you know. You either love it or you hate it. And so this was an introduction to recursion. I'm actually not going to ask you too much about n-queens, because you just coded it up. And the only way you learn about the n-queens problem is by coding it up. On the other hand, what I do expect you to know is recursion, obviously. And so, for example, here's like a little piece of recursive code, right? The code to compute a factorial. So I expect you to be able to reason about pieces of code like that. Small pieces of recursive code. I might give you something like this. Of course, not have the word factorial there. Some other thing and say, okay, what is this function evaluated on 5 or something like that? And it'll be a little trickier than that, but those are the kinds of questions that I expect you to know. I expect you to be able to reason about recursive code. And there are lots of good examples of that in the book. So in chapter 3, if you look at the exercises, there are examples of recursive, like there's some recursive function and it says, what is the value of this recursive function on blah. Does that make sense? So questions like that will be asked. You should know about it. Yes? Yes, yes. Sorry? Well, I'm just reason about it. Well, you should be able to evaluate the code. Yeah. By reason, so let me show you an example of that. So I'm going to actually not talk about nqueen specifically because I think that was mostly an introduction, but something like this. So a question like this that I had asked. Sorry, let me zoom out. So here I said, I want to print an array in reverse, and I'm going to define a recursive function, and I give you 3 different examples, snippets of code, and I say which is the one that's actually going to do it. And I expect, so this is what I mean by reasoning about code. You have to tell me which of these actually will print an array in reverse. Yes? How are you supposed to explain? Well, you must have figured this out. It's not obvious. So maybe you'd say, for example, you could say in option R is not true because if the array has size 1, then it doesn't print anything. Right? That's one sentence that explains away why R is incorrect. You could do that. Or you could just say that I ran this example on this piece of code and look at all the function calls I got. Just follow, just show me. If you show me an example where each code fails and one code passes, that's good enough for me. Yes?
So you could basically solve the question, explain your answer, not using just normal English, but you could just show in bullet points what you did for the chunk of code.
Yeah, I mean, I would say that the easiest, the most convincing explanation would be, here's an array. I ran this array on that. Look, I didn't get the right answer. I ran this array on it. I did get the right answer. And I ran this one, and I got the wrong answer. Right? That's convincing enough for me. I just want to make sure that you have some logical train of thought that led you to the answer, not that you just guessed. It's fine to say that I just eliminated these choices. Right? You don't have to give me a proof. But I don't want a magnum opus. I don't want you to write 2 pages. I'm not going to read it. So I have a rule for this. I will read 5 lines, 5 sentences. Or if you just show me pictures, you can say, look, I don't know, something like. So we did. Actually, here's an example of something that we did. So I think we were looking at what the yellow code was doing, which is if I is equal to j return and print reverse aij minus 1, print aj. And then you could show me the trace of what was called. You say, oh, print reverse a04 on this would call this, and this is what got printed at every step. Something like that. A small picture is good enough. Does that make sense? Yeah? That's also fine. I mean, if you just do it by elimination, it's fine. I just want to see that you're reasoning about code. Now, I just don't want you to randomly guess and say, well, you know what, I think that this is correct because, and then you throw the whole kitchen sink of what you know at me, which is typically, okay, so why am I making this multiple choice? Because, I'll be honest, I don't want to read all the crap that you can write, which is usually what I get if I say, oh, give me an explanation for this, and you will tell me everything that you know, and some of it is going to be correct. So how do I decide how to partially grade you? With multiple choice, you have to commit to an answer, and you have to give me an explanation. That's it. Right? So obviously, if you know the answer, if you have some reasoning, then just write down that reasoning. Does that make sense? Questions? Just write down the reasoning. Just give me a reason why this code is incorrect, or this code is correct, or whatever. If you say, I ran it on this, and look, I didn't get the right answer for these, then that's a good enough explanation. Yeah?
You go through the answers and find the right answer, first. We still have to go through the other 2 and prove they're wrong.
No, I mean, it's fine if you can. I mean, what would be problematic is if you say, oh, I ran it on this array of size 1 and look, it works. Well, maybe all of them work on arrays of size 1, right? Yeah?
Since we can use pictures as a form of explanation, then I ask, how much room is there for...
There is room given for you for the answer in the sheet. You guys are like lawyers, right? You're trying to find all kinds of loopholes. And I'm trying to be as reasonable as possible, and then it's like, well, can I do this? Can I draw the picture towards the end? What if I hold it up and I see it in the back? Does that count? Come on, guys, be reasonable, right? There's some space there, use it. You know, obviously, if you know the answer, you don't have to give a long explanation. Something like this, pictures like this are good enough. Yes? Does it matter? So why? Now I'm curious. Why does it matter? But the exam is not even there. Don't you have to wait to get the test before you can decide how to allocate your time? Are you going to figure out a strategy right now? Huh? Humor me. So how? Okay, so suppose I told you it was 50. How would you prepare differently if I told you it was 10? Tell me. Yes, yes. Okay. But how does that affect how you prepare? Don't you have to learn the material anyway? Yes? Okay, there's one question on the midterm. Go ahead. Yeah?
I don't necessarily agree with what you're saying. When I get to 50, you could say, oh, if I get stuck on one bench, since there's more, I'm going to skip it, I guess.
Just study. Just study. Just learn the material. It's not that hard. Yeah. So questions like this. I give you a snippet of code, and I say, what does this snippet of code do? How do you reason about it? Well, you run it on an instance, and you can show me, you know, what they call the box trace. You say, this call led to this, and this got printed here. This led to this got printed here, so on and so forth. That's a good enough explanation. Okay, so basically those are questions on recursion. And again, it's good to do the exercises that I did in class, and the book has more. So that's a good way of learning how to reason about recursive code. So I did more examples of recursion, which I'll sort of end for now. The next thing that we talked about, so after talking about recursion, we talked about abstraction. So the example of abstraction that we had was, we said, you know, if you're doing the Queen's problem, and you wanted to check if you're given an array of queens, given as an array of column positions and row positions, and you wanted to check if there's any attack, you could run a double for loop and then write whatever logic you need to check if the queens are attacking. But the right thing to do would have been to actually abstract this as a separate function, right? And that's how you get modularity in code. Now, obviously, it's much harder for me to check how you do abstraction if I don't ask you to code. But, so, like regarding abstraction, I guess, I don't know if you remember any of this, but we said, you know, it's useful to define a class queen and have, you know, a specific isAttacking function here that you can use to make your code simple. And so I expect you to at least know these concepts well enough to understand things like inheritance and override. That's sort of what I expect. So, any questions? So presumably much of this you should have absorbed by doing the assignment, right? There's not, I mean, there's no concept to learn from a book. It's actually, you code it up and then you realize how it works. But remember we had this notion of we would use a superclass chess piece and subclasses of queen and knight to make the code clean. And the best example of this is probably in the solution for homework 2, which actually has all of this stuff coded up. One of the things that that does come up over here, and I want to sort of spend some time on this, is these questions on inheritance, right? So I have a class A, and I say public void foo, are you in A? And then class B extends A, so that's inheritance. And then, maybe I'll zoom in a bit. And then there is an override, right? So I can define a function foo in the subclass that overrides the superclass. And then there were these examples of snippets of code where you had to say what gets printed. I expect you to know this. I expect you to be able to reason about such snippets of code. Basically, at some level, the entire exam is about reasoning about small snippets of code. And sort of the most interesting example over here is where you have some kind of polymorphism or what's called subtyping. So these are sort of straightforward, right? You define a variable of a particular class. You say, okay, you define a reference for a particular class, and you say var is equal to new A, and var.foo, or you do it for B, it's quite clear. But what happens if you define your reference, a variable of some class, but you instantiate something of another class, right? And so it works when the reference is of the superclass and the object is in the subclass. But if you actually have a reference of the subclass and you create an object in the superclass, then this throws a compile error. Right? So being able to reason about things like this is important. Questions? And if you're having some, well, I've given you the answer here, obviously. But if you're having some trouble sort of reasoning about this, I'd actually suggest just write up a little Java snippet, a piece of code that just does each of these things and look at what the output is. And hopefully you use some of this in homework 2 anyway. So it shouldn't be too hard. But I expect you to know this. Yeah? How do you explain something like this? Okay. You could just write, this is just common sense. Everyone knows this stuff. No, so in this case, var.foo, you have to say, look, the object is of this type. So, okay, so for example, why does this throw a compile error? It's not, I don't think it's just common sense. There's a reason why it throws a compile error, yeah? Yeah, that's the reason, right? And that's a logical reason, whereas in this case, there's no compile error because you can use a reference of the superclass for a subclass object. And when you call var.foo, the appropriate function to call is determined at runtime, depending on the type of the object. So what I just said was an explanation. And it was 3 sentences, less than that. Yes? My explanation sounded like you can do this in jargon. So learn the jargon. I don't know. It's you can do this because there's a logical reason for doing this, which is that references, can point to subclasses, but not to superclasses. Yeah.
I will say, to make another note on that, you may feel like it's obvious, but in a lot of languages, it's not what happens.
That's true. Exactly.
So showing that you understand how it works in Java means that you actually understand that concept. Well, in C++ is different, or some other language is different. So knowing that is not just an option.
Yeah, exactly. Which is why using the jargon, I think, sort of tells me that you understood what is going on. Exactly. So yeah, this doesn't happen. In C, you may not be able to do stuff like this. You can probably do a lot more. You have pointers. You can do whatever you want, but it wouldn't make sense. Yes.
How technical does our explanation have to be?
I just gave you the explanation right now, right? Webcast, go look at it, memorize that, write it down. Right? An explanation that this compiles because I know it compiles is not valid. Obviously, you shouldn't be compiling that during the exam, So you don't have that reason instead. Instead, you have to give me this reason by subclasses, superclasses. You use the term inheritance and override, right? And then I know that you understand what's going on. Yeah? Sure, you can use is an instance of this, is an instance of that to explain it as well. Yes. Wow, I didn't think that this was that confusing, honestly. But okay, good. So there were more examples of things I did with chess pieces to explain this, and I don't want to get into that. But what is important, and we sort of discussed this, and even though it's hard to ask specific questions about this is a concept that I want to reiterate, that there's this notion of abstract data types and data structures, where what you think of is you think of some sort of specification of type. Like as we thought about linked lists and stacks and queues, there's just a specification. You want to be able to insert, you want to be able to delete, or you want to push, you want to pop. That is distinct from the actual implementation, right? So you can implement lists in multiple ways, through an array, through a linked list. You can implement stacks in multiple ways, and those give you the specific data structures or the implementations, which is distinct from the specification, the abstract data type, right? So stack by itself doesn't tell you how it's implemented, right? So it's important to know the distinction between that. And so, for example, if you just look at a class sort of, you can use an interface to do this, but just think of if you looked at a class and you looked at the fields and you looked at the methods without seeing what the actual implementation is, that is sort of telling you the specification, what you can do with an object in this class. So for example, we'd say we'd like to insert, delete, and find. That's what a list data structure does. And we had discussed one way to do it is to basically store it as an array of strings. So you can maintain, let's say, a list of strings as an array of strings, and you know how to insert, find, and delete. I expect you to know how to be able to do these things on an array. It's not hard. You hopefully should have learned, you should know this. And as we discussed, one of the issues with implementing a list, which basically does an insert, delete, and a find as an array, is what? Yeah. Exactly. You need to know the size of the array. Or you have to sort of keep resizing the array if things become too big, which is exactly why we use linked lists. So we had then, from there, sort of so a problem with the implementing string list as an array is we don't know how many objects we need to store, right? And that's why we use a linked list. And sort of, it's important that you understand this, right? I could ask questions about that. Why implement things one way as opposed to another way? So this is sort of reasoning about the implementation. And this sort of segues into the fact that you have to then understand how memory is stored in the system to be able to understand, at least at a deeper level, how linked lists work. And so any questions at this point? Okay. So what we did is we then talked about how arrays are actually stored in memory contiguously. Again, this is an important concept that you should know. An array is contiguous in memory. So if I want to double the size of an array, I have to go and find a chunk of memory that's bigger. So for example, if I want an array of 100 blocks, whatever that block, maybe 100 ints, and I want to resize that to 200 ints, then I have to go and find some place where there's 200 empty spaces, which if you think about it, for a list is not really necessary, unless you're worrying about efficiency. But ignore efficiency for now. There's no need to have all of the list be contiguous in memory. And that sort of leads to this notion of, there's a notion of an object versus the reference or the location in memory. So this is very important, and you should know this if you don't know it already, is that in Java, what you have are references. Student S is a reference to a student object. It is not a student object itself. In C or C++, student S actually is an object. Yes, so in Java, when you say student S, that is merely a reference to a student object, which you then create by calling new student. So this is very important. In C and C++, there's a distinction between the object and its reference. And in Java, it's kind of, there is really no distinction. All you have are references to objects. Yes? Yes?
Is there like distinct difference between the term reference and pointer, or do they mean the same thing?
They mean the same thing, but, well, yes and no. So at a conceptual level, they're the same thing. But when you say pointer, it usually refers to the C thing, which is a pointer. You wouldn't really call this a pointer. You'd call it a reference. So I think it's mostly in the terminology with respect to the language. Because when you think pointers, you think that you can manipulate pointers. Yeah.
So I was going to say in C++, in addition to pointers, there's references, which are an entirely separate concept.
Yes, but in this context, I want you to think of them as the same thing in C and sort of C and Java. The distinction between the object and the location in memory that it actually lives in. And so that's where we come to this, where we say there is a distinction between an object and a reference, as I've said multiple times. And let me just let me skip this and we'll sort of come back to it. The point is, in Java, when I say student S, all I have is a reference. So it's sort of initialized to null. And then when I say S is equal to new student, it creates a student, and then sort of the location is stored there. And so what is really important is that when you do things like this, S is equal to new student, and let's say there's a constructor which put the ID, major, and year there, 1, 5, and 2015, and whatever. When you say S is equal to T, you are only equalizing the references, not the objects. Right? So when you say S is equal to T, and you print S.ID, you get 2, but not because the entire object was copied. Because essentially what happened here was something like this. This is what S initially references, 1, 5, 2015. T is referencing 2, 6, and whatever. When you say S is equal to T, this sort of gets lost there, and S and T start pointing to the same thing. So if I now change S.ID, I am also changing T.ID, because they're pointing to the same thing, right? Which is important. Before this step, if I change S.ID, I'm not doing anything to T.ID. But after this, they're both pointing to the same thing. So at this point, actually, it's sort of worth mentioning, now that you've done Lab 4, this is kind of like a memory leak, right? Because you cannot access this portion of memory anymore. You lost the reference to it. So Java does garbage collection. What that means is Java will figure out that nothing is referencing that and go and free that memory. In C, there is no garbage collection, so that memory just gets blocked. And that's a memory leak, and Valgrind is used to find those. Yes?
I was going to ask, does Valgrind delete it for you, or does it just find it?
I believe it only finds it for you, but I'm not sure. I think it only finds memory leaks. Yeah? Does not doing garbage collection? So garbage collection slows things down. So Java code is slower than C code. So if you really cared about efficiency, which in many cases you do when you're doing large-scale code, then you would go for C so that you don't, so that you don't pay the extra cost of garbage collection. Yeah? Not really. I mean, if you write C code, let's just say that these were two objects and these were two pointers, right? And you said, okay, let's say you got this through a malloc. That would be sort of how you would do it, right? You get malloc, and then you got one pointer, you got malloc, another pointer. You equalize the pointers, so you lost whatever S was pointing to. You don't really have to do anything, because that will just be allocated by the operating system for this process, and gets freed when the process ends. It's like wasted memory, right? And if this was running in a for loop, you could use up a lot of memory that you're actually not utilizing, and that might then cause the program to crash, which often happens if you have really bad memory leaks. Yeah?
Does garbage collection in Java work as like a loop in the background looking through your memory, or does it automatically just notice once something's been like switched and a variable is in place somewhere that it just knows?
I think it periodically goes and checks. So that's actually, you could ask the question of how does Java figure that out? And that is actually called a graph problem. So it like looks at all the references, looks at all the memories, and it creates this structure called a graph, and then goes and figures out what portions of memory are not being, that have previously been allocated, don't have a reference to it. Questions? I'm not going to ask you ins and outs of garbage collection, of course, but.
So in C, if you did this, and instead of making them pointers, you made them student objects, and setting them equal to each other
would actually set them equal to each other, exactly. So if these were student objects, and you did S equals T, then there is no pointer. The object actually gets copied, which is convenient. In Java, you don't have this copy object, and it's a pain, right, if you actually want to copy something. In C, that's an explicit copy. So if you copy an array, then it's actually going to go and copy all those elements. Yeah. In some sense, I don't know. So I learned C before I learned Java, which I think was a good thing, because then this distinction between objects and references is clear early on. And then when you learn Java, you're like, oh, okay, there's a reference. Whereas if you learn, say, Python or Java first, you don't really learn about this distinction. So you think, oh, two objects. I make S equals T. It should obviously be copying the object. But no, it's copying the reference. Right? So another thing is, of course, that's why in Java, you always pass by reference. In C, if you actually have an argument with an object, the whole object gets passed, which is why you use pointers to pass things around them. So it is very important that you learn this, not just for the sake of the midterm, but for the sake of your general career. Knowing this is going to really help you. And people ask questions about this in interviews, and in general, as a computer scientist, you should know about this. Okay? Yes? You mean do free and then and then set it to null? No. So if you let me write this down, and maybe that would clear things up. So you have some pointer. I don't know. I'll just say some int star ptr. Ooh. No. So let me write something down, and you tell me if this is what you're asking. So then you do, this is equal to some malloc. And then you have something here, and then you do a free, and then you do that, right? Can you switch the last two commands? Because if you switch the last two commands, then you're freeing a null pointer. And that will throw an error. Or it should throw an error. So you can do something like this. Suppose you did this. Free pointer plus 1. And then let's just say you did this instead of this. Instead of this, you did this. So you can think of pointer is pointing to some block of memory which you got through malloc. What if you did this? What happens? Yeah? The memory is free, but the pointer is still there. It's like you're freeing, so pointer plus 1 is something like this, right? That's what pointer plus 1 would be. Because so if you go and look up, and it's really funny, if you go and look it up, the C standard says we have no idea. It actually says you shouldn't do that, and we don't know what happens. The behavior is undefined, which is why you can get into lots of trouble. So if you free a pointer which was not the result of a malloc, then the behavior is undefined. That's what it says. And so that's why you have to be very careful with pointer arithmetic, because you might say, oh, this is, I have this, and then I have star PTR2, and then maybe I made, PTR2 is equal to PTR plus 100, because I wanted to save the first 100 blocks for something, and I want to free up the rest of the memory. You might think you might want to do something like that, so you say, oh, I'll just go and free PTR2, but that's not valid, because PTR2 is not the output of a malloc command. So somehow in the internals, it remembers which is the output of a malloc command, and so you should only free pointers. You do this so that if there's any subsequent code that uses PTR, maybe something that tries to dereference it, you get an error then, right? If you leave that pointer hanging around, suppose you did not do this, right? So let's say you didn't have this command, right? So you have that. So let's say what you had here was, I don't know, 42. And so suppose you do free and you do star PTR, you will have access to 42, even though the memory has been freed. Unless something, it could get overwritten, anything could happen. Does that make sense? You can dereference portions of memory that are freed. So the only thing that free does is it lets the operating system take that memory, but you can dereference it, which is why you set the pointer to null. Now if you did something clever like this, like, oh, I'm going to add that, you might have freed pointer, but you still have pointer 2, which is not pointing to null, and you can get yourself into all kinds of trouble. Does that make sense? Yes? Okay. Yes, you need to know pointers. Yes, I will ask questions about pointers. Sorry. People seem to hate pointers, but that's life. So in, yes? So you cannot, I mean, you cannot pass, okay, so if you had some struct student, and then, I don't know, you had some function which maybe computes a grade or something, which says int grade struct student s, then you cannot pass a pointer to grade. You have to pass the object. I mean, that checking C will do, right? You have to give the right argument. So if you really wanted to pass a pointer here, then you would say struct, student star s, and then you would be able to pass a pointer. Depending on what the function definition is. This is just like, any other language, right? So when you define a function with arguments of certain types, obviously C is going to go and check that type. It's just that if you had this, you could still send a pointer to an int. Send it a pointer to an int. Because pointers of different types are still pointers. So that's one sort of exception to that rule. You can send pointers. And it will just interpret that pointer as a pointer to a struct. Yeah? Kind of? Okay. So going back to sort of this notion of references and objects not being copied, I had questions like this, right? So you have two students, S, this is again Java code because it has new, S is equal to new student, T is equal to new student, S is equal to T. What's going to happen? Yeah, go and do these exercises. Make sure you know the answer and make sure you know why the other answers are wrong. Because I will ask questions like this. So from here, basically, we then go on to linked lists. So let me get that out. So I expect you to know the code for a linked list. I will ask questions about it. I'm not going to ask you to write down the code. So use your notes or whatever, right? So you have, you have the book or whatever with you. So you should be able to look up the code of a linked list, or at least remember it if you do. Where remember that what you have are nodes, which have a val and a next. Where next is a reference to the next node, and you link together by doing something like node n1 is a new node n2 is a new node, n1.next is equal to n2. This is the most important linking operation here, and then you can ask all kinds of fancy questions about that. So I expect you to, again, reason about snippets of code that are moving references around. So if I say, look, this is what I did, which picture represents what's going on in memory, you should be able to say something about that. Or not something, you should be able to tell me the right answer. Okay? Hopefully, I mean, again, if, yes?
Are linked, just side question relating to earlier, are linked lists abstract data types, or is that a data structure?
Once you talk about the implementation, it's really a data structure. It's really a data structure because I'm telling you how this whole thing is set up. You should really think of list as the abstract data type, which is implemented as a linked list. And again, like the only way to learn about this is not to read it through a book, but to code it up yourself, suffer null pointer exceptions, and then finally it starts making sense, which hopefully happened in homework 2. At least if you didn't learn, at least you suffered the null pointer exceptions, which is an education in itself. So with linked lists, we have an insert method, which basically inserts at the head. We have let me actually do this the other way around. So we have the insert method, which basically takes the new value, creates a node, sets that to head, and then points, latest.next points to head, and then you update head. Does that make sense? So if you had something like this, you insert 42, then you create this node 42, head now points to this new node, and if you kept doing this, then you would get some picture like that. Right? So if initially you had v1, v2, v3, v4, and you inserted a new val, head was initially pointing here, but after this process, new val points to here, and head now points to new val. Yes? Yes. Sorry. So let's go back to the insert function. So in English, what does the insert function do? It creates a new node with this value and puts it at the head. So it has to update the head and make sure the linked list is connected. So there are basically just 3 sort of statements here. Node latest is equal to new node. So it creates a node. Then it says latest.next is equal to head. Right? The previous head. So latest now points to the previous head. And then head is now latest. So it updates the head. So in terms of a picture, which is unfortunately messy right now, but hopefully will make sense. Let's say this was the linked list initially. Wait, I can just do this. Yes. This was the linked list. Head was pointing to v1, to v2, to v3, to v4, and then null. This was your linked list. Now you did an insert of new val. What you want is for that new node to now point to the original head and head to point to the new node that you added. Make sense? Because you always add, we discussed that always add at the head of the list as opposed to the end because it's cheaper to add at the head of the list. It's more efficient. So what happens initially, this new node gets created. So maybe I will sort of go through this in this way, if I can. So node latest is equal to new node new val. That created this node. That's what latest is, right? Then latest.next is equal to head. So this is latest. Dot next was initially what? When you created the new node, what was latest.next? Null. And then latest.next, which is this pointer, points to head, which is the original beginning of the list. So then this link gets added. But head is still pointing to here, and it has to point to there. So then you say head is equal to latest, and then you get that. And so now the linked list has been updated. Yes?
How would you split
Previous meaning? If no, what do you mean by implement head and previous? So right now we've implemented insertions.
I mean like next. Like previous, we kept next.
You mean how do you implement a doubly linked list?
Yeah.
So let's come to that. Okay, we'll come to that. But you really need to understand how insert in linked lists work. Insert and deletes. Yes? You should know how to, yes. You should know how to implement a doubly linked list. I'm not going to ask you for code, but I could do something like say, here's a doubly linked list, and I want to insert this node. Which snippet of code actually does it accurately? So I'd give you a bunch of examples and say which of these is correct. So again, insertion is at the head of the linked list. Questions? Questions about insert? Again, hopefully when you coded this up, or if you coded it up, you would have learned, which is the best way to learn linked lists. And so there is this important feature in a linked list, which is, or function that's often called traverse, which is important for finding. And so in a traverse, you start at the head, so current is equal to head, and current keeps going to current.next until current reaches null, which is the end of the list. Right? So this is how you have a pointer or a reference current that just sort of walks through the entire list. So for example, if we looked at this linked list here, current would start at the head, which is here, and then current.next would go there. Then current.next keeps updating itself until at some point when current points to that, current.next is null. So it ends, right? Or rather, current is equal to current.next, and then current becomes null. Yes? In this case, so in this case, why won't you get a null? Okay, so there is one issue. If the list is not empty, actually no, this code is always correct. You'll never get a null pointer exception. Because before you actually access valid next, you first checked whether it was null. Remember, the checking whether it was null happened before you did any of this. So you'll never have a null pointer exception with this code. If you did this check afterwards, you could have a null pointer exception. Right? So you could have an equivalent, you might think it's equivalent, you could say while 1, so have an infinite loop there, but break if current is equal to null over here. Does that make sense? Maybe I'll write this. So what if I did the following? I say, again, void traverse node current equal to head while true. So ignore the print statement. That's not important. Current is equal to current dot next, and if current is null, break. Is this a correct traverse function? Think about it. Yeah, I could ask questions like that. Is this a correct traverse function? No. Why? Yes? Is empty. If head was actually null to begin with, this throws a null pointer exception. So if list is empty, that would mean, so the list is empty, head is null, this code throws a null pointer exception. So how do I fix this with one line? Yeah? I could move that to there. That would be one way of fixing it. Yes? Well, while head is not equal to null. That's true. You could do that, or you could just put, yeah. Although you're checking the same condition over and over again, but that would be correct. So you could replace this by while head not equal to null. Yeah? Yes, you. This would also work. Both of them would work. Well, when you put current is not equal to null, you go back to the old code. But this basically says you're just going to check this condition over and over again, which if it's false, you wouldn't have entered the loop. And if it's true, then it's the same thing as doing while true. Yeah, I could ask trick questions like that, just in case you wonder. Yes? Exactly. You could put an if statement over there and just check if head is equal to null, then just like return. Exactly. So hopefully you get the idea. Yes? Would I ask why this works? Yes. Well, I mean, I wouldn't ask why this code works. I would say this code fails or this code doesn't fail. Here are 3 reasons. And you have to tell me which one. Or most probably what I'll do is I'll give you 3 snippets of code like this and say which of these works. Questions? Okay. So that's insert in linked list, insert in traverse, which is also the traverse leads to find. And so that's a big distinction from deletion. Yes? So best examples to use. So start with the empty list. Most codes throw errors on the empty list. And then that usually, usually when you have a null pointer exception, it's either because it's the beginning of the list or the end of the list. While things are in the middle, often the code will work. So empty lists, it's unlikely that you'll actually not find the error. If you use a list of like size 2, 3, 4, it should be correct. Like if it works for all of those, it usually is correct. One thing to think about is often if you have these what we'll see, like in deletion, you're maintaining 2 pointers, previous and current, right? So you have to be careful when you maintain 2 pointers that neither of them throws a null pointer exception. And so those are things to check. And usually if the 2 pointers are close to each other, then a small enough list will show you the error that you have. So we had discussed deletion. So deletion is important, obviously, in linked lists. I expect you to be able to know how to delete in linked lists. And so we had these questions on, so to delete 42, you need to know the previous node. You need to have a reference to the previous node, not to the node itself. Right? Because to delete that, you have to have a reference that will jump over that, and you need to know what this node is. That is probably the single most important thing to know about deletion, is to delete a node, you have to know the previous node. Yes? Okay? And so if you have previous and you have current, then you would just say, to delete current, you do previous.next is equal to current.next, and that jumps over that node. This does not always work because the head is a special case in deletion. Right? And that's why I have all these questions. Deletion of the first node or the head is a special case where you just do head is equal to head.next. Right? So deletion actually requires both these. If you're trying to delete the head, you do head is equal to head.next. If you're trying to delete some other node, then you have to find the previous node for that, and then do previous.next is equal to current.next. Yes? Yes, question? You can do previous.next is equal to previous.next.next because current is previous.next in this example. Yes. So you can chain the .next together, which was actually somewhat the content of this question, which is to delete 42. What is the minimal set of references you need? And you only need n1. You don't need n2 or n3 because you can always get n2 or n3 by doing n1.next or n1.next.next. And so there was the line of code that actually deleted, and it's n1.next is n2.next, or n1.next is n1.next.next, which does the deletion. So that was deletion. And we went through an explicit code that deleted in a linked list. I'm not going to walk through it entirely. But it's there in the notes. All the notes are there on the website. Please go and look at that. Make sure you understand the deletion code, right? Because I will ask questions about this. And it's again important to understand. By the way, the reason that there was a question of why it throws a null pointer exception, it was essentially because there was some place where you had to check whether current was null. So again, when you have 2 pointers, 2 references, make sure that you understand when both of those become null. And it's often at an empty list or when the code runs to the end of the list. This is usually where you get null pointer exceptions. Questions? Okay. Then there were some sort of neat tricks like manipulations of lists that we went through. We only went through one, but which is how do you print a linked list backwards? And there was a recursive piece of code to do that, right? So for example, if you want to write backwards, starting from some node, if the node is not equal to null, you write backwards of current.next, and then you print the value. Right? So this is sort of an example where you have both recursion and linked lists mixed in the same question. And you print the entire linked list backwards by doing backward of head. Right backwards of head. Yes? You should be able to understand such snippets of code. And we also went through an example where actually a piece of code that reversed a linked list. So I'm not going to tell you this, but you can also use a recursive function to reverse a linked list. You should think about how you would do that. Yeah? It looks like you never hit the print. I mean, okay, so maybe you have a return over there, but would you have to switch these statements? So what happens is, let's say you start from here, right? So current is head. You're going to go here. You're going to first call write backwards of current.next and then print this value. So to do write backwards here, you're going to go there and call write backwards next of this. And then you go there and call write backwards next of that. And then you go here and you call write backwards of this. Now what happens over here, write backwards of current.next is null. So that call returns nothing, and then you would print. And then you would go back, and then you would print that, and print that. Yes?
Do we need the return statement for this equation?
No, you don't need the return statement. Yeah. I just sort of put it there to make sure that the code ends right there. Yes?
Just a comment, if you did substitute statement that's in the if statement, it would print it forwards.
Yes, exactly. If you kept these two, if you switch those, you would print it forward. This is an example of a question I might ask. Right? If I switch the statements, what is it going to do? It's going to print forwards. Again, the best way to understand this is to run the code, like manually. Yes? Print when current equals null. So when current is equal to null, nothing happens. Right? So in an empty list, this doesn't do anything, which is what it should do. Rather, it's exactly what it shouldn't do. Yes? Question? No. Because you could have a return statement somewhere in the middle just to sort of exit the code at that point. Yes? When you insert the data in the opposite direction. Well, I mean, think of this as I give you a linked list and I want you to print it in backwards order. The linked list has an order, and I just want to print that in backwards order. You're right that this order would be the order in which things were inserted, but you could have had deletes and you could have all kinds of things. So it doesn't specifically say anything about what happened, but you're right, yeah. But yeah, write backward is for the linked list. And so we had discussed another function called reverse that reversed a linked list. This was not a recursive piece of code, but it's useful. I think I'll just walk through this piece of code because it's one of those things that's not tricky. I mean, it's tricky to come up with, but in the end, you should be able to reason about this. So you start with a node previous and null. This is extremely common in linked lists, that you would have a previous and a current, and they kind of march together. And this is so that you have access to sort of the previous reference for the current node. So while current is not equal to null, so it's important to have that condition, because you should think that, okay, what happens when the list is empty? Nothing should run. So usually whatever condition is there in your while loop should force an exit if the list is empty. So I'm just going to have a temporary thing called foo, which is current. Maybe it's worth, let me just draw something here. Okay, let's do something like this. So let's say this is your linked list at some point, whatever, and this is previous. Now previous points to current, which then points to all this other stuff. What you need to do is to reverse this pointer, right? You have to reverse this pointer. And that's what happens when you set current.next is equal to previous. So that's going to reverse, or I'm sorry, that hasn't changed this pointer. That points this thing over here. You have to then change this. Okay, sorry. Let me start all over again. when this function is running on a particular previous and current, this pointer has actually already been flipped. Now I've confused myself. Okay, let me start all over again. Again. So this is current, and this is previous. And at this point, what has actually happened is that everything over here has already been reversed. What you now need to do is to make this point over there. But right now, this is pointing here. So actually, at this stage, in the middle of the algorithm, the linked list has been split into two parts. All of this is pointing in this direction, and whatever is here is pointing forward. Does that make sense? So it's actually split the linked list into two parts. The way it fixes it is by saying, well, now current.next should point to previous. So that will fix that. Right? So that will fix that. And then you shift previous and current one step forward. And that's why you set previous equal to current. And you do current equals foo because once you've switched this pointer, you might have forgotten what's there, so you store that at current.next. Foo. And so foo would actually be what's pointing one step ahead. Does that make sense? So you sort of have three pointers simultaneously at that point, three references. And so you have to be careful about null pointer exceptions and all, but this works. Finally, when this code ends, you have to reset the head to be the very last node, and that's what this does. Go through the snippet of code if it doesn't make sense, and make sure you can reason about the fact that it's correct. Right? Run it on an empty example, run it on an example. Remember, without this statement, so in this code, every statement is necessary. If you remove any one of them, you have some kind of error. Think about what kind of error that could create. Like if you didn't have this, well then you would have forgotten what current.next is. And if you didn't have this, then the head is set incorrectly. The head is actually at the tail of the list, not at the beginning, right? After the reverse. Make sense? You can also write recursive code for this in this way. You can think of writing a reverse which is recursive. And so I think I went through like a detailed example of that as well. So again, look at the code and make sure you can understand how it works. Variations of linked lists. Yes, I will ask about variations of linked lists. Or I might ask. That's maybe what I should say. Because I can't ask everything. One is having a tail reference, which I think we saw when we wanted to implement a queue using a linked list. You have a tail reference, right? So you have a head and you have a tail. And now you can insert at either end. You can insert here or you can insert at the tail. And this is useful for maintaining queues. Right? That's sort of its main usage. You might ask, why not always have a tail pointer? And that's because the more stuff you add, the more code you need to keep everything updated. Another example is the circular linked list, which goes in a circle. So there is no null at the end of the list. So think about how you would insert into a circular linked list. It's not as easy. It's not as easy to insert, because if you simply insert in a node and you make it point to the head, the loop actually has a problem. There's still a loop. Does that make sense? So if you inserted as before, so what you would do is you would change that. You'd say, oh, okay, I'm going to put something here, and this point's there. But this is not a valid circular linked list because you have to switch this pointer. Yeah?
Do you have to have a tail pointer in that then?
You don't. There's an interesting puzzle question that comes up from here. So it's been asked at interviews. I guess maybe they don't do it anymore because it's now become fairly common. So here's the problem. You have a linked list which might have a loop. Okay? And you have to tell whether the linked list has a loop or not. Except I only give you two references. That's the only memory you can use. Make sense? You have a linked list. I give you the head. The linked list may or may not have a loop. I want you to find out whether it has a loop or not, and I give you 2 references. That's all you can do. You can only march those references. You can do whatever you want with those references. Those are the only variables you have. Maybe 3, whatever. It's some fixed number. How would you solve this if I didn't have that restriction? How would you find out if there's actually a loop in a linked list? Okay, this is the problem. I give you a linked list, find out if it has a loop. Maybe I should ask that question. Yeah?
If you save one of the objects in the one linked list in the same node and then traverse through the node and check that one node is equal to many other nodes.
So you store a node, and you traverse through the linked list to see if you see that node again. When do you stop? But if it has a loop, there's no null. Does that make sense? In this, there's no null. So let's say you start here. You're going to keep looping through this, and you'll never find it. If you've heard the answer, don't blurt it out. Don't spoil it for the others. In the back, yeah? So right now, again, think of the question where I actually I'm not having any restriction on how many references you can have, right? So do whatever you want, but solve the problem for me. Yes?
Have a specific sequence of the first 3 things you can have, and then once you find that sequence again, then it's a loop. But if there's a pointer at the end.
This is much more interesting, so let me do this for a while. Okay. I won't tell you the answer to the main thing, but at least it's a good exercise to come up with the answer here. So let's say you have a linked list like this. Wait, so someone else had a suggestion? There were multiple. Yeah.
While current.next doesn't equal head, or current current.next doesn't equal null, and then just traverse through it.
While current.head, you'll have an infinite loop, though.
Well, why won't current.next equal head at some point?
It's not a circular linked list. It only has a loop. It's not a yes, if it's a circular linked list, that's exactly what it has a loop, which means that this is not a circular linked list. It has a loop, though. Right? Maybe I should explain the problem again. Your linked list has a loop. That means that it's it's like a circular linked list with some other stuff attached to it. But you only have the head. Yeah? So if you have a double for loop, here's what's going to be the problem. Let's say there are a bunch of nodes here, right? You're going to start here, and then you traverse the list. And it's just going to keep going on and on and on. Which reference? So let's say you have 2 references, right? So initially, let's say this is reference 1. Now reference 2 is going to keep marching. That's an interesting thought. Interesting. And if there is no loop, then they hit null. You just, yeah.
They're the same, or if one
Yes. It has a loop. Interesting. Yes. Well, you imagine two checks, right? If it skips two, then you check both. By the way, yes, so that is basically the solution that uses only 2 pointers. It's called the tortoise and the hare method. You have a tortoise and a hare running through the thing, and then you use it. But there is a way of solving this without much, an easier way is to use arrays, right? As you go, again, this uses a lot more memory, but use an array to just store all the references. And that way you can just check if 2 references in the linked list are the same, right? So that would be sort of the obvious solution. Or it's not that obvious, but that would be one solution. And then you say, well, how do you decrease the memory? Does the discussion make sense? Yes? What are we trying to find out? Good. Does the linked list have a loop? Does the linked list have a loop? Yes? It's a singly linked list, so there's no going back. That's the whole problem. That's the whole problem. But you can solve this using arrays. All you do is walk through this and store all the references. And anytime you see a reference that you've already seen in the past, so you can do this with enough memory. So whether you understand the clever solution that uses 2 pointers, you should be able to understand the simple solution, which is store all references in an array and check every new reference during a traversal. Does that make sense? So you store an array of references, and as you see a reference, you go and copy it into this. And as you copy everything in, finally, when there's a loop, you'll see this reference, but that's the same as this reference, and you can go and check in the array whether it's the same. Bummer, I gave up a good question. You've been going over it in your sessions. Okay, good. Yes? Well, the problem is it uses a lot of storage, though. It's actually not one reference, but it's storing all the references. So it's using many references. Think of it, it's an array of references, and then you might have to worry about dynamically allocating. You don't know what the size is, so you might have to keep doubling it. So it's a much more messier solution. You're only marching one at a time, but you're storing everything. So if you think about the total number of variables you need, it's actually a lot. Yeah, so think about that. Okay, circular linked lists and doubly linked lists. Doubly linked lists have 2 pointers, a previous and a next. And so I expect you to know how to insert and delete into these. At least you should be able to figure out the code. Right? It's somewhat painful, but it's not hard. Basically, you have to update all the pointers. And if you do that, you'll know why people don't use doubly linked lists because it's just a pain to handle all the pointers, or why you shouldn't use doubly linked lists. Okay, then circular linked list, doubly linked list. The next topic that we had covered were pointers. And the important things you need to know about pointers are the address operator, called the referencing operator, that actually gives you the address of a particular variable. And then there is the opposite, called the dereferencing operator, star, which basically, given a pointer, gives you the content at that location. You need to know what star is, you need to know what ampersand does. And the best way to go through this is through the code that I had shown during class. I have all that code on the website. Go and run it and make sure that you understand why things are outputting the way they're outputting. I guess there's, so yes, is this, any questions on this? Yeah?
And I guess this is a specifically C question, but the ampersand, does it return a pointer or does it return a reference? And this is more about difference between reference and
It returns a pointer. I mean, I guess it returns a location.
is the pointer more than just a location?
So think of a pointer as a variable that stores a location. They're sort of the same, I mean, yeah. Does that make sense? Yeah. So, and so there were multiple examples that I had. I'm not going to go through all the code now, also because I don't have my laptop with me. But you should be able to, hopefully, if you go through those examples, you should be able to understand how these operators work. Star and ampersand. And what is important to know is that arrays are just pointers. So when you say int foo10, it allocates 10 blocks of memory, and foo is the pointer to the beginning of that block. And so we had this discussion of pointer arithmetic, which is very important. So foo plus I is the same thing as foo I, and is actually the pointer which is foo plus size of int times I. Yes? Pointer arithmetic, very important. Lots of examples in the code that I put up that has lots of examples of pointer arithmetic, which you should go through. Remember, a pointer can be cast to any type. I can take a pointer to an object, to a struct, and I can cast that as a pointer to an int. Right? So the arithmetic changes. Again, there are examples in the code. Please go and look at them. Someone had their hand up? Yes? In this case, foo is int. Foo is an array of ints. But it's the size of this, exactly. Size of whatever foo points to. There's also, so yeah, pointers, very, very important. Please understand pointer arithmetic and how it works and how it relates to arrays. And in C, remember that there is no new command, and so if allocation is done through malloc and calloc. You should know about those. Hopefully the lab teaches you a lot more about that than I said, but you should understand how malloc, calloc, and free work. Pointer arithmetic, arrays, malloc, calloc, and yeah, so just to reiterate, there is declaring a pointer. You need to know what a pointer is. You need to know what the address operator does, the ampersand operator. You need to know what the star operator does, which is a dereferencing operator. Understand how arrays work. Array is just a pointer. And understand pointer arithmetic. That's, what does foo plus I mean? And there are enough examples in the code that I put up to explain all of this, and understand malloc and contiguous allocation calloc. So that's a fair bit of stuff to learn about pointers, but yeah, so hopefully that should be enough. I do have links to some references online, which you can also read up. But I think if you can understand the output of all the code that I put up, I think you should be fine. There's not much more to know. The final topic, so I'm not going to ask you about queues. The final topic is stacks. And so stacks are pretty simple. There's a push and a pop and a peek operator that looks at the top of the stack. You need to know how to implement a stack. Remember, there are two implementations. One implementation is through an array. That's the array-based implementation. And one implementation is through a linked list. You need to know both these implementations because I could ask questions like, does something work in one implementation but not the other? What is the difference between these? So for example, in an array-based implementation, you have a bound on the size, right? Because the array might fill up. You don't have that problem if you have a linked list. The sort of the last topics that were touched on in stacks specifically was an algorithm to check whether parentheses are correct using stacks. You need to know that algorithm. Again, I don't mean that you need to memorize the algorithm, but you need to understand how it works. And remember that basically what it does was for every symbol in the string, it pushed an open character onto the stack, and when it's a closing character, it tried to match with the top of the stack. That was the basic idea. That's how the stack-based algorithm works. Go through the notes. I'd ask questions about how the stack-based algorithm behaves. You need to know this. I could ask questions like this. I can ask questions about, here's an algorithm we discussed in class. Does it have this property? Does it behave like this or that? Yeah? Questions? And then sort of the last thing in stacks was postfix or reverse Polish notation. Yes, you need to understand how RPN works. You need to understand how to convert one expression into RPN. By understanding how you need to be able to do it yourself. And you need to understand the code that we discussed using stacks that figures that out. Right? So we had discussed sort of multiple things actually. So I think I'll talk about both of them. One is, how do you evaluate RPN? So given a postfix expression, how do you compute the value? And there was a stack-based algorithm to do that. Right? So go over that. Make sure you understand how that works. And then there was another algorithm that actually, hang on, let me put that over here, sort of flying all of this by you, but just so that you remember that something like this was discussed, how do you convert a normal expression into a postfix expression? That's also a stack-based algorithm. So two stack-based algorithms here. One is to evaluate an RPN, and the other is to convert a normal expression into an RPN. Both of them are based on stacks. Please go over them and understand them. And in stacks, we also discussed how you can use any code that does recursion and convert it to a stack-based algorithm. Yes, you also need to understand that. So in stacks, just to go back, what do you need to know? You need to know basically what a stack does. That's simple, push and pop and peek. You need to know the different implementations of a stack, the array-based and the linked list-based. Closing parentheses, checking parentheses, and checking reverse Polish notation. And finally, how do you do recursion with stacks? And that's it. Questions? Yes?
This is about the assignment.
Yes?
But I found a few inconsistencies with analysis.text. So like, for example...
Wait, come and talk to me. Yeah. Yeah. Labs are not on the midterm. Stuff that's covered in the labs are not on the midterm.